Hello, everyone. Today we're going to talk about prion structural dynamics and disease susceptibility. So why do we study prion dynamics? Well, we study prion dynamics for a couple of reasons. First, it's important to know that normal prion proteins, called PrPC, can change conformation to deleterious prions, PrPSc, when in the presence of PrPSc. They aggregate and form fibrils that cause transmissible spongiform encephalopathies, called TSEs. A grouping of invariably lethal neurodegenerative diseases of these TSEs include Creutzfeldt-Jakob disease, mad cow, and Kuru. We know currently that there's a dynamic species barrier, but the mechanism for conversion from PrPC to PrPSc is still unknown. So uncovering this can lead to targets for treatments, which is in a special need of urgent solving because just a few years ago in 2014, the USDA recalled 2 tons of beef in fear that deleterious prions would spread to human beings. So our proposed hypothesis is that differing amino acid constituencies will accordingly modulate different PrPC structural dynamics as caused by natural selection pressures. So the first thing that we did in order to analyze prion structural dynamics is perform in R a deformation energies comparison. We found a few things. First, we found that we had large confidence intervals across all of the ITASR predicted protein structures, which suggests that there are numerous possible tertiary conformations in the N-terminus region, approximately Residue 21 to 121, that all the species can take as a whole. We also found that there are high deformation energy values, or these local flexibility values, in the N-terminal region between residues 96 and 125. This region, again, is incredibly flexible. However, in rabbit, there are 2 sections that are unique to it. We find that in rabbit prions, there's a unique region of flexibility at the end of the C-terminus compared to human and rabbit, which are the other 2 species that we studied, as well as right at the beginning. Right at the beginning, we call this region the tail club region, and we'll see what that looks like a little bit later on. So just as a side note, we know that from least to most susceptible to prion disease, it goes rabbit, human, and bankful. So some general observations that we found were that the deformation energy pattern was actually found in an inverse order to disease susceptibility, or an inverse order to the aforementioned. We found that the largest magnitude of energy spikes in the disordered region, the N-terminal region, went bankful, human, rabbit. Most of the residues in these spiked regions actually became glycines, or were glycines, and we noticed specifically in rabbit that it exhibited magnitudes of local flexibility by a margin greater than 1, which contradicts our earlier hypothesis that a more rigid structure would prevent PrPC to PrPSc conversion. So in essence, we found that decreased N-terminal residue flexibility correlates to increased disease susceptibility. So then we performed again in R a residue connectivity analysis. Here you can see the tail club regions and the disordered regions. We found 3 conclusions. The first is that when we have a less dynamically compact and more locationally diverse tail club region, it contributes to prion disease resistance, theoretically. We also found that increased residue flexibility in that disordered region may actually contribute to prion disease resistance, and PrPCs with more equivalently sized and closely connected communities, or sections of residues that most closely interact with each other, are more resistant to conversion. In human, we can see that in the cross-correlational community number 1, the initiatory sequence right at the beginning of the N-terminus is where the tail club region lies. It interacts closely with communities 5 and 6, which will be analogous to the rabbit and bankful communities we'll see later. This includes pleated sheet 2 in humans, and it also lies right after an island of stability. We know that the N-terminus region is, although a disordered region, actually is incredibly stable. In bankful, we found that the tail club uniquely encompasses pleated sheets both 1 and 2. In all species, but namely in bankfuls, we found that community number 5 dominates the C-terminus region, which is analogous, like I said, to the region number 5 that we described before. It encompasses 1/2 of the first alpha helix and 2, and then all of helix 3. In rabbit, we found that most of the communities compared to human and bankful were larger and more evenly spaced and more closely connected. We found that communities 1 and 3, again analogous, experience abnormally large deformation energy spikes and thus local residue flexibility. That includes that valine, number 244, and the far reaches of the ordered region, the C-terminus. And that community number 1 does not exist actually as a tail club compared to the other two. In fact, it's far more electrodynamically disconnected than its interspecies counterparts. And we can see that through the matrix to the right, where we find that most of those residues don't actually move parallel or anti-parallel with one another across all the conformations. They're more neutral in that sense. The next question that we wanted to answer, and we did this through the CAMSOL server provided by the University of Cambridge, was a dynamic versus solubility analysis, trying to see how does solubility contribute to PrPC structural dynamics. Our answer was that similarities, as aligned by CAMSOL, indicate that there's no direct link between conversion resistance and local protein flexibility. And understanding this, we named 5 different regions that were the same across all of the species. We named them A through E, and they ended up being analogous in both in terms of where they were located, as well as in terms of the magnitude of their hydrophobicity. Again, in the graph, you can see here that a higher value indicates a greater degree of relative solubility, while lower degrees, those negative values, indicate high hydrophobicity. Among bankful, human, and rabbit PrPC, again, we see equivalent sections both in location and in magnitude of their solubility scores. However, in rabbit, again, having its own noteworthy constituencies, we find that at the very end of the C-terminus, in that same region where it's very high in terms of local flexibility, that connects also to the tail club region, is a region that I termed N sub R, and this N sub R region is uniquely hydrophobic. And so, subsequently, hydrophobicity may play a part to some degree in terms of the PrPC to PrPSc conversionary process. So in sum, we can see here that the disordered region of human PrPC, obviously, based upon the way that we are analyzing it, seems to play a role in the docking mechanism that elongates a particular PrPSc fibril. The most energetically stable formation aligns the prion to the side of the fibril, and it's flanked top and bottom by the regions of high flexibility, those spikes that we saw in earlier graphs of glycine 58 and glycine 94 that flank that top and bottom. So subsequently, we believe that more energetically stable formations, even if they do align on those deformation energy spikes, tend to correlate to a lesser resistance, whereas more flexibility tends to indicate that whatever species has that prion will be more resistant to getting a transmissible spongiform encephalopathy. And so there are a few next steps that we plan to undertake in order to continue this research. The first is what we're doing right now, which is a suboptimal pathways calculation. The literature indicates that methionine probably plays a role in the conversionary process, and so subsequently, we want to see what sets of residues or what lines of residues most closely interact with one another, as opposed to just performing a holistic residue community approach. We'll also do much more precise docking calculations in terms of doing the same community analysis that we did previously with each of the ITAS or predicted structures, as well as an energetics analysis to find where those regions of local flexibility are. So thank you for watching the presentation. I'd like to acknowledge the NIH, INBRI, the Center for Undergraduate Research and Scholarship at Creighton University, obviously Creighton University, as well as all of my lab mates, Stephanie, Ian, Armand, Hannah, and of course, our lab lead and our advisor, Dr. Patricia Soto of the Creighton University Physics Department. So I hope you enjoyed. Please feel free to leave any comments in the chat function, and I'll be prompt to answer any of them. So again, thank you, and have a good day.